Supposedly I'm sharing, yeah. All right, so yes, thank you everyone. I know it's getting late, so I will try to keep this brief. But so I'm just going to talk to you today about something a little bit different to what you've seen so far, but the use of molecular hydrogen as a way of tracing turbulent regions in galaxies in a way to suppress star formation from AGN feedback. So, yeah, just a quick word on AGN feedback. So AGN are thought to be somewhat influential in stellar evolution because, in galaxy evolution, because they have quite a large amount of energy, and if any of that makes it back into the surrounding host, you would expect it to do something. But despite the fact that we know the AGN properties and the galaxy properties seem to be linked, actually establishing these feedback mechanisms somewhat uniquely is quite difficult still. But there is an exception to this ambiguity, and that's in a class of radio galaxies which show extremely strong molecular hydrogen emission, as well as really weak star formation. And these are known as MOHEGs, or molecular hydrogen emission galaxies. So MOHEGs can have up to 20% of their mid-infrared luminosity from the molecular hydrogen. And the nice thing about molecular hydrogen is that it has to be quite warm to emit. At least 100 Kelvin, if not higher, depending on whether you're looking at rotational or ro-vibrational lines. And MOHEGs in general, on the right-hand side, you can see as the red triangles fall quite far below the Connecticut-Schmidt relationship. So they have an awful lot of gas, but they're not doing anything with it. It's just kind of not forming stars. So in these galaxies, what we find is that since they're all strong radio objects, it's likely that the molecular hydrogen is being excited through shocks, possibly from the radio jet. And also the molecular hydrogen has quite wide line widths, suggesting that there might be high turbulence. And it's this turbulence that could suppress star formation. So what we want to do is we want to take one of these objects as a test case. We want to look at it with JWST with a high angular spectral resolution and see if we can see structures consistent with shocks and see if the turbulence makes it down to the small scales. What we had before was we had Spitzer and symphony data, which you can see on the top right, but JWST gets much better resolution. So you can see the equivalent line with JWST at the bottom right. So you can really see the improvement. And we take NIRSpec and MIRI IFU data and combine it with JVLA, which is radio data, of 3C326N, which is the best studied MOHEG that we have. And as a bonus, we get to compare the rotational ro-vibrational molecular hydrogen, which is important for high redshift studies, and I'll get to that later, and also ties into ELT. So 3C326N, very quick summary of what it is. So it's a giant radio galaxy, 3 × 10 to 11 solar masses. Very low star formation rate, but the AGN itself is actually quite weak, at least radiatively. So it's got a very strong radio jet, but you're not got enough photoionization to cause the molecular hydrogen emission that we see in this object. So the most likely candidate for causing the molecular hydrogen in this emission in this object is indeed shocks, and the radio jet seems to be the most likely candidate. So I don't expect you to read all of this. I just wanted to demonstrate just how rich this data set is. There is an awful lot of it. So you've got this, to the top is NIRSpec, and then the first 3 channels are MIRI. And we've got an absolute ton of molecular hydrogen lines, and as well as a few ionized ones. And you can see in red some CO bandhead absorption features. So in total, we have 19 ro-vibrational lines and 3 rotational ones. And we also have 3 ionized transitions that we can spatially resolve, with 1 extra that can only be picked up on the total integrated spectrum. On the right-hand side is just the continuum of this galaxy, seen with NIRSpec. So you can see it's quite a regular galaxy. It doesn't have any weird morphology, maybe slightly inclined. And we do get clear detections in every channel of MIRI and NIRSpec except for channel 4. So the first thing we do is try to work out our 0 point, our redshift, so we can get the velocity of everything in comparison. And the best way to do this in this case is to use the CO bandhead absorption, because this belongs to the stellar component, not to the gas one. So what we do is we take templates for CO bandheads, we fit every spaxel individually, and we find, as you can see in the top left, that we get very little offsets in terms of velocity across the galaxy. So we see very little in the way of rotation. Now, this is expected because this object's a slow rotator, sorry. But what this means is that we can combine all the different fits together into one probability space to get a really accurate redshift. You can see really high redshift here. But this is what we then use as the 0 point for all our other studies. So then we get on to fitting all the different molecular line transitions, as well as the ionized one. So as a very brief overview, we fit 1 or 2 components compared by the Bayesian information criterion. If it's multiple component, you fit them simultaneously. The only thing that's a bit non-standard is that we use non-uniform redshift priors for the 2 different lines. All this basically means is that we punish it for the 2 components being too separated, because if they get too far apart, they're probably not from the same line. But we find that almost all the lines, except for 1, show very, very similar structure. And what you can see right away here, because all of these are just 1 spaxel fits, getting down to the 100 parsec scales in this object, is that even the narrow component has extremely large line widths. So straight away, we can say that there is far too wide a line to allow for star formation in these scales. So this is consistent with the fact that there is turbulence suppressing star formation in this object. Now, I'm not going to go through everything because there's way too much in this galaxy, but one of the nicest things we saw, which was not obvious in the previous data, is that this object seems to contain a huge cavity, which is very consistent with the idea that there is there is a shock mechanism. Because if you look at these here as 3 different lines, you've got a rotation line, ro-vibrational line, and a recombination line. And in all of them, you can see this kind of in the north, this hole in the center of what is otherwise a nice bidirectional outflow. And the thing is, you can see that along the edge, you also have these clumps, and the different lines seem to get to different parts on the edge of this bubble. So what we take this to be is a cavity that's being inflated by interactions with a radio jet. And this is supported by the fact that when we take a look at the JVLA data, we find that 50% of the flux is missing. So between the solid core, which is the white contours there, which is a bit difficult to see, sorry, but and the larger scales, we lose half our radio flux. And this is consistent with a more diffuse radio emission, which JVLA would not see, such as radio plasma inflating that cavity. Just as a next quick thing, we also just compared this galaxy to the Schmidt relationship, just to see if it does indeed fall below, and we find that it does. So if we use CO, which is a cold gas tracer, that we find that we fall about 23 times below the Schmidt relationship, being very conservative about it. If we switch to H2, which actually traces the warmer 100 Kelvin gas, as I was saying earlier, which seems to be a larger component in this object than the cold gas, you get further away. You get 100 times below. And this is all being quite conservative. The offset gets much larger if you make different assumptions. And as a final thing, what we then do is we compare the rotational ro-vibrational lines. So we account for the differences in angular resolution between MIRI and NIRSpec, and we extract the same transitions from the rotational ro-vibrational for different areas of the galaxy. Because while you want to always look at the rotational lines, these, if you want to look at turbulence, these get redshifted out of JWST and the ELT very quickly. You can't go to very high redshift at all if you want to use these as traces as turbulence. But the ro-vibrational ones, the 1,0 lines, trace much hotter gas. Because of that, they're much bluer. Unfortunately, you can't say that these trace the same environments. So what we find is we pick different areas in the galaxy. We find that indeed, there are different ratios. As you go to different areas of the galaxy, your environment does change. However, the change isn't that big and is actually smaller for larger redshifts than the systematic uncertainties that you'll encounter. So all in all, for high redshift objects, you can probably use the ro-vibrational lines as stand-ins for the rotational ones, which is very important when it comes to studying this kind of turbulence and feedback at higher redshift with the ELT. Because the ELT will allow us to start to get the flux limitations that we need to be able to observe these at much higher redshift. And I'm not going to go too much into this now, but for AGN feedback in general, it also offers us a lot of compatibility with the VLTI, which is another way another thing we've been using to try to get feedback to the galaxy through dusty outflows. But I'd be happy to talk with anyone about that if they wanted to see it. And there's also been some discussion at this conference of tying the ELT into the VLTI in general. So I'm probably already pretty late. So I'll leave the summary here. But yeah, does anyone have any questions?